All right, folks. Instructional video for Monday the 11th. What I want to do real quick is just, again, revisit what we talked about Friday, and that is what is a bond? Down here on the notes, it's a chemical bond is this mutual attraction between the positive nucleus of an atom and the electron cloud of another atom. Coulomb's law, opposite charges, oppositely charged regions of different atoms attract one another, and then there's some repulsive forces that keep them from collapsing completely into one gigantic atom. As far as why bonding happens, why do bonds form? They form so that atoms that are unstable in their neutral form, they don't have the full S and P sublevels. They don't have that noble gas electron configuration. By sharing electrons with each other or transferring electrons, are able to get a full outer shell. So that's why bonding happens, to increase stability and to give elements that don't have the noble gas configuration a way to get those extra electrons they need to become stable. Okay. As far as how they form, we talked about ionic versus covalent. Ionic bonds form when the metal donates electrons to the nonmetal. The metal becomes positive, the nonmetal becomes negative, and then those oppositely charged ions cluster together in gigantic clumps like this, where the positive and negative ions alternate, and the total charge of this entire sample, the net charge, if you added up all the positives and then subtracted all the negatives, would be 0. Okay? Covalent, that type of bond happens when electron clouds overlap. So if we scroll down through here for a second, and this is just an illustration. So this is an atom with P sublevels. Here's your PX, your PY, and your PZ sublevels, okay? Here's an atom with an S sublevel, and you can see they overlap right there. That overlap is the bond, and that is a pathway for electrons to be shared between these two atoms. This overlap right here is a P and a P sublevel overlapping, okay? So you can have atoms or electrons shared between these two atoms, electrons shared between these two atoms, electrons shared between these two atoms. That would be covalent bonding. And the term co helps us to remember that nonmetals, when they bond with other nonmetals and they overlap and share electrons, are only stable when they are bonded. The moment they unbond, they become unstable again. Okay? So, in summary, what we talked about last week was the kind of bond can be determined by the combinations of element types that we have. So if it's a metal and a non-metal, we said that that's ionic. If it's all metals, we said it's metallic, and that's a special kind of sharing. And then covalent is all non-metals. Okay? If you noticed last week, there's a little bit more detail in our note packet about using what we call delta En to determine bond types as well. So this idea here, this symbol delta En, delta stands for the difference in electronegativities. The difference in electronegativities. So how do we calculate the delta En? Well, the delta En is calculated by taking the electronegativity values for any two elements that are going to bond, any two atoms that are going to connect with each other, whether that's ionic or covalent, taking the higher electronegative value minus the lower electronegative value. So delta En is high electronegative minus low electronegative. You can almost think about it as a absolute value. We are only concerned about the difference. It doesn't matter which direction we figure that out. We just want to know what the difference is. So if we take an example of nitrogen and oxygen here, nitrogen has a value of 3.0 and oxygen has a value of 3.5. You could find that right on your periodic table It's the number in the bottom right-hand corner of the element boxes. So each element in the bottom right-hand corner on your periodic table has an electronegativity value. That value is 0.5. So what does that mean? How does that help us determine the bond type? Well, there's a scale, okay? We start with non-polar covalent, which means equal sharing of electrons. Electrons are equally shared between two atoms if the delta En, the difference in electronegativity, is between 0 and 0.29. So anything less than 0.3 is what we call non-polar covalent. Electrons are equally shared. We'll talk about the dipole thing in a minute. Polar covalent is if our difference is between 0.3 and 1.69. So anything between 0.3 and 1.69 requires a dipole that's unequal sharing, which means one atom is going to have the electrons that are being shared. They're going to spend more time around one atom than the other. And what ends up happening is you end up with one atom being more negative and the other atom being more positive. If we think about that, the atom that has more control over the electron spends more time in its cloud, is going to behave as if it has more electrons than protons. It's going to be partially negative on that side. So the higher electronegative atom is partially negative if the difference is greater than 0.3. And then the lower electronegative atom is going to be partially positive because it's going to behave as if it has less electrons than protons. To show that, to demonstrate that, we put in a symbol called a dipole. If the difference in electronegativity is between 1.7 and 3.3, which is just the highest that you can get, so basically greater than or equal to 1.7, the electrons are transferred and it's ionic, it would need a dipole as well. So delta En in bond types: nonpolar covalent, which is equal sharing of electrons, no dipole, the delta is between 0 and 0.29. Polar covalent, unequal sharing, needs a dipole, 0.3 to 1.69. And then ionic, electrons are transferred. That's if our delta is between 1.7 or more. 1.7 or more, okay? So when we look at the dipole, this is the symbol for the dipole, and that's a really, really bad looking dipole example. So let's redo that real quick. So the dipole always points from the low electronegative to the high electronegative, and it exists if our delta En is greater than or equal to 0.3. So if you have a polar covalent or ionic compound or bond, polar covalent or ionic bond, you're going to have a positive end and a negative end. We put this vertical line on the tail of the dipole to show that this is the positive side. So the dipole is always pointing from the positive to the negative, from the lower electronegative to the higher electronegative atom. And what it's trying to show us is that the higher electronegative atom, that's the direction the electrons are being pulled. So the electrons are being drawn to that side, okay? As far as our assignment goes today, I want you to work through 1 through 4. Make sure you understand the definition, so just hit the text box feature here and type in your answers. And then down below, you're going to use the electronegativity table here or on your periodic table to figure out the deltas. So if we look at this real quick, let's use this as an example, this hydrogen and oxygen example. hydrogen has a value of 2.1, oxygen has a value of 3.5. So the delta En would be equal to, sorry, this is, so the delta would be 3.5 minus 2.1. So you get a 1.4. That puts you in the polar covalent range. So that means that the type of bond we have is polar covalent. And the dipole is going to go from the lower electronegative to the high electron. So your dipole would go from hydrogen to oxygen. So you can just draw the dipole over the bond like that. Okay? Now, anything that is polar covalent, or if we look at lithium and nitrogen, lithium has a 1.0 value. Lithium has a 1.0 value. Nitrogen has a 3.0 value. That means that you're going to be in the 2.0 is going to be your difference. So you're going to be ionic. Okay? That's going to be ionic. Lithium, nitrogen. Your dipole for an ionic compound always goes from your metal to your nonmetal. The nonmetal is always the one that is getting the electron. So ionics always go from metal to nonmetal. If there's a non-polar covalent compound, you would just put NPC. That would just be NPC, and you would not need a dipole. Okay? So go ahead and try that on the CAMI assignment. Please make sure that you get that done prior to class tomorrow. If you have any questions, shoot me an email. See you tomorrow morning.